Okay, so I'm going to talk about two important classes of matrices in this video, or maybe just one important class because the second important class is a subset of the first important class. Anyways, so before I do that, I need to give you another sort of canonical form. Any matrix, so this is a fact, and you can look in the book for the proof. Any matrix is unitarily equivalent to an upper triangular matrix. To an upper triangular matrix. Okay, in other words, what that means is that for every matrix A, we can write this, I'm going to use the book's notation Q times R times the Hermitian adjoint of Q. In other words, we are the Hermitian transpose. In other words, we take the transpose, or we do the transpose and then take the complex conjugate, and this is upper triangular. Okay, so that's just a fact. You can look in the book for the proof of this. Okay, and this is called the sure decomposition of A. Okay, so I'm going to give some definitions and then prove. I'm going to give a definition of a normal matrix and then prove some things about a normal matrix. So, definition: a matrix is normal if it commutes with its Hermitian its Hermitian transpose. Okay, so i.e. AHA is equal to AAH. AHA is equal to AAH. That's what it means. A matrix is normal if it commutes with its Hermitian transpose. Okay, so here is a fact. Let's see, where do I want to write this fact? Because I need to have some proof. I'm not going to prove this fact, but I am going to write over here if R is upper triangular, so like this one. If R, I'm just going to kneel down here to make sure I don't go on a diagonal. If R is upper triangular and it is normal, then it is actually diagonal. So in other words, a normal upper triangular matrix is diagonal. Okay, and again, normal means this right here. So a normal upper triangular matrix is diagonal. Okay, so here's how we can use that fact, and we're going to prove something, sort of a good theorem that's going to be. I remember in the previous video I said that there's only a few theorems, or there are some theorems that say if a matrix satisfies this simple property, then it is diagonalizable. I'm about to give you one. I'm about to be able to show you that if a matrix is normal, then it is diagonalizable. Okay, and that's actually an if and only if statement, but we'll get to that in just a minute. Okay, a matrix is normal. So let me say this as a theorem. A matrix is normal. Let me just say it this way. A is normal. A is normal if and only if it is unitarily equivalent to a diagonal matrix. So if and only if A is equal to Q times D times the symmetric or the Hermitian transpose. So the theorem here says A is normal if and only if it is unitarily equivalent to a diagonal matrix. So D here is diagonal. This is unitary, meaning Q, H, Q is equal to the identity matrix. Okay. And because we're in the context that we are, all of these are square matrices. They're n by n matrices. Okay, so why is this true? Let's assume, so this says A is normal if and only if this is true. So there's two directions to prove. Let's assume A is normal. So assume that A is normal, so that A is equal to AH. Then by sure, okay, what is sure? This is the sure decomposition here, okay? Then by the sure decomposition, what do we have? Well, A, again, I can write like this. So AHA, if this is if this is A, and I take the adjoint, so notice what's going to happen. If I do AH, remember what we do, it's going to be, writing from the left to the right, it's going to be the adjoint of this matrix, which is just Q, times the adjoint of R, which is RH, times the adjoint of Q, which is QH. So actually, this, if this is equal to A, then this is equal to AH. Okay, so I'm going to leave that there. So now AH we can write as Q, Q, RH, QH times A, which is just Q, R, QH. Okay, and again, using the associativity of matrix multiplication, QH times Q is equal to the identity matrix. So this is simply Q, RH times R times QH. Okay, so that's the left-hand side. Now, if I do A times AH, well, A is Q times R times QH, and then again, if I do AH, it is Q RH times QH, and now this is equal to Q times RHR times QH. And since A is normal, these two things are equal to each other. So these two things are equal to each other. This is just AHA. This is AAH. By normality of A, they're equal to each other. And so these two things are equal to each other. Okay? So therefore, I'm going to write this and step out of the way. We've got Q, R, H, R, QH is equal to Q, R, H, R, QH. Sorry, I got this backwards. This is RRH. Okay, and so this down here is RRH. Like this. Okay, so now what's going to happen? So we want to say that, well, so therefore these two things are equal. That's the same, and that's the same on the outside. So therefore RHR and RRH are equal to each other. That's not something that we can always say when we're dealing with matrix multiplication, because we're not always able to invert these, these matrices here and here. But we are in this case. So this fact is true from what we've seen up here. Notice what happens if I multiply on the left. These two things are equal. So if I multiply on the left by QH, I'm going to have this. And if I multiply the right, both sides, multiply on the right, both sides by Q, I get this. QHQ is the identity matrix. QHQ is the identity matrix. In other words, those cancel, those cancel, those cancel, those cancel. And so we're going to get RHR is equal to RRH. In other words, by the Schur product, by the Schur decomposition, R is upper triangular, and we've just shown that it's normal. RHR is equal to RRH, and this fact here says that an upper triangular matrix, it says that if an upper triangular matrix is normal, then it's diagonal. So in fact, R is equal to a diagonal matrix. Okay, now I will let you prove the other thing for yourself. If A is equal to if A is unitarily equal to a diagonal matrix, in other words, if this is true, then just prove that A is normal. Just compute AHA and AAH, and you'll see that they're equal to each other. Okay, so what can we tell from this fact? Well, if A is normal, then A is equal to Q D QH. Okay, so we know now that A is unitarily equivalent to a diagonal matrix, and we saw in a previous video that the eigenvectors of D, the eigenvectors of D are the unit basis vectors. And so if I look at A times Q times the unit basis vector, well, I can write this as, using this decomposition, as Q D QH times QEK, like this. That's equal to the identity matrix, so this is just equal to Q D EK. Let me put arrows over my vectors here. Now, what is DEK? Well, DEK, as we saw in the previous video, is just equal to lambda K times EK. So this is equal to lambda K times Q times EK. So in other words, all of the vectors QEK for K equals 1 to n, these are all eigenvectors of the matrix A. There are n of these vectors, and they are linearly independent. That's what I said in the previous video. So therefore, if A is normal, it has n linearly independent eigenvectors. And that theorem that we proved in the last video says that a matrix is diagonalizable if and only if it has n linearly independent eigenvectors. Okay, so that's just another stupid. Why did you? What? Okay. Wow. What are you on crack, dude? Okay, so there is even a more special type of matrices that are a subclass of normal matrices. These are called Hermitian matrices. So a matrix, so this is a definition. A matrix, and I'm pretty sure I've given this already, a matrix is Hermitian. Another word for this is self-adjoint. A matrix is Hermitian if it's equal to its Hermitian transpose. AH is equal to A. Okay, so of course, if AH is equal to A, then AH times A is equal to A times H. So every Hermitian matrix is a normal matrix. And so what this tells us is that every Hermitian matrix has n linearly independent eigenvectors. Okay, and it's very easy to just look at a matrix by inspection and determine whether or not it's Hermitian. Just see if the reflected entries are going to be equal to each other. Determining whether or not a matrix is normal, it requires one computation, or maybe two, computing AHA and AAH. But it's not something like we don't have to compute. We don't have to do any computations of eigenvalues and eigenvectors. and then take those eigenvectors and see if they're linearly independent or anything like that. We can just do these products, and that's not directly involved with eigenvalues or eigenvectors, but this is a test that will tell us if a matrix is normal, and if a matrix is normal, then it's going to have, if a matrix is normal, then it's going to be diagonalizable. Okay, but again, a matrix is Hermitian if it's equal to its own Hermitian transpose. So that's a lot easier to check. We can just look at it and check. And as we will see in this class, a lot of the matrices that we make, that a lot of the matrices that come up in applications turn out to have this symmetry property. They turn out to be Hermitian. Okay, and we could just, like, we're going to be constructing the matrices that we're going to be analyzing. So from the construction of the matrices, we'll be able to tell that they're Hermitian and therefore have linearly independent eigenvectors and are diagonalizable and so on and so forth. But here's a fact about Hermitian matrices. So I don't know if you really want to call this a theorem. I'm just going to call it a fact. The eigenvalues of a Hermitian matrix are real. So the eigenvalues, if A is Hermitian, I'm just going to abbreviate this as Herm. If A is Hermitian, then the spectrum of A, that is a set of eigenvalues, is a subset of real numbers. So the spectrum of A are real. The spectrum of a Hermitian matrix is real. Okay, so why is this true? Well, let lambda be an eigenvector. So we've got lambda. So lambda is equal to lambda times v. And I'm not going to write this down, but I'm going to tell you what v is. V is the eigenvector of A associated with lambda that has unit length. So if you do the inner product, the v with itself is just equal to 1. Okay, I can now put lambda on the inside. And so now we're going to have lambda v, comma v. All right, so this, what is lambda v? Well, it's just equal to AV, because lambda and v are an eigenpair. Now, in general, this is equal to v times AHV. That's just one of the properties that the Hermitian adjoint satisfies. But notice in this case, we're assuming that A is Hermitian, so AH is actually equal to V. And so now this, AH, the Hermitian adjoint of A is just equal to A. So this is V, comma AV. Well, what is AV? That's just equal to lambda V. So this is V, comma lambda V. And now I'm going to put it down here. To pull this out, we do lambda bar V, comma V. So V, comma V, again, is just equal to 1. And so this is equal to lambda bar. So we have lambda is equal to lambda bar. Well, that is just another way to say that a number is not that a number is real. If you have a complex number and it's equal to its own complex conjugate, then it's a real number. Okay, so this shows that all of the eigenvalues of a Hermitian matrix are real. Another thing that I want to say here, let me make sure I have this correct. Okay, fact. If A is normal, so I should have said this in the context of normal matrices. If A is normal, then its eigenvectors are orthogonal. They form an orthogonal set. Okay, one of the reasons that I didn't say this, well, never mind. If A is normal, then its eigenvectors are orthogonal. Okay, why is that? Okay, so sorry, I'm going to have to go from right to left and bottom to top, maybe not the most ideal way to do things, but that's what we're doing. So if I look, so what are the eigenvectors of A? So if we do A, my claim is that the eigenvectors are going to be A times QEK. Okay, remember the EK is a kth standard basis vector. Okay, now if A is normal, we can write it. It's unitarily diagonalizable, so the Q here is the Q from the unitary diagonalization. So A is equal to Q D QH, and then times Q e to the K. QH times Q is the identity matrix, so this is simply Q D e to the K, or not e to the K, but EK, because QHQ is the identity matrix. And as we have seen before, D times e to the K is just lambda K times e to the K. So this is going to be Q lambda K times Q e to the K. Okay, so this says QEK is an eigenvector of A. But what is QEK? This is just equal to the kth column of Q. So this is lambda K times little q. But these are orthogonal. What does it mean for a matrix Q to be a unitary matrix? It means that its columns form an orthonormal set. Okay, so the eigenvectors, if you look at a set of eigenvectors associated to each eigenvalue for A, and A is normal, we know that set is going to be orthogonal, and then we can normalize them all so that it's actually orthonormal. Okay, so if you have a normal matrix, we know that its eigenvalues are diagonalized. Sorry, we know its eigenvectors are orthogonal to each other. And since a Hermitian matrix is normal, it also follows that a Hermitian matrix, the eigenvectors of a Hermitian matrix, are also going to be orthogonal as well. Okay, and so that is going to let us prove the following fact here. Okay, actually, before I prove the following fact, I need to give you another definition. I really want to use this entire side of the board over here. So I'm going to give a definition over here. So if you have a matrix, we can define this function. You know what? It's not going to show up enough over there. Okay. The field of values for a matrix is okay. So we're going to look at this function. The book calls it mu, so it's mu of x. X is going to be an n-dimensional complex vector. This is equal to the inner product ax x divided by x comma x. And then the field of values is going to be the range of this matrix A. Or sorry, the range of this function mu. Now oftentimes, I mean, we can always define this as long as x is not equal to a zero vector. We can define this for any vector, or sorry, for any matrix. But it really is only applied in cases where A has some structure. In particular, usually we want it to be normal because, usually we want it to be normal for this to be something that we're going to use. But it doesn't have to be. This definition, can be applied to any matrix, but it's just typically what we're going to sort of concentrate on using it is going to be for when the matrix is normal or even indeed Hermitian, which is what we're about to use. Okay. Because what we're going to show is that the maximum value of this, if A is a Hermitian matrix, the maximum value of mu is going to give us the biggest eigenvalue for the matrix. Okay. So, this blue marker is not really doing what I want it to do. Let me see if I can find another blue marker. sorry, I cleaned my office and now I have no idea where anything is. And my office really isn't even that clean right now. Okay, so let lambda 1 greater than or equal to lambda 2 greater than or equal to lambda 3 greater than or equal to ... lambda n be the eigenvalues for the Hermitian matrix A. For, I think I'm going to end with this mark. I'm going to stop this marker. Well, for the Hermitian matrix A. Okay, so in other words, A is a Hermitian matrix, and we are ordering the eigenvalues in decreasing order, or non-increasing order. Okay, so we could have repeated eigenvalues here. Okay, but since A is Hermitian, we know that all of the eigenvectors are actually orthogonal to each other. Okay, so let those be the eigenvalues for the Hermitian matrix A. Then, actually, let me finish the statement of this with the blue marker, and then I will retire the blue marker. Then lambda 1 is equal to the maximum of all of the vectors in Cn of this field of values function that we have. So I'm going to write it as AU, comma U, divided by U like this. Okay, so in other words, if we form this is called the Rayleigh quotient. If we form this and then look at all over Cn and find the biggest one, or find the U that makes this the biggest, that is going to be our lambda 1. Okay, and we actually know that this is a maximum and not just a supremum. The reason is because we can replace this. We could just say, I'm going to erase this, but we can also write this as the maximum of U in Cn, such that the 2 norm of U is equal to 1. And now this is AU U. Okay, and now we're looking at, this is a continuous function of the variable U over a compact set. And so it attains both a minimum and a maximum. Okay. Okay, so why is this true? So I'm actually going to leave this here because I'm going to generalize this fact and write it below here. But what I want to do is I'm going to have to erase the entire right-hand side of the board, and I'm going to prove this. This is a very, very nice fact about Hermitian matrices. And the only point at which we're using the fact that the matrix is Hermitian rather than just being normal is that to show that the eigenvalues are real. It's to be able to have an order of the eigenvalues. So in a certain sense, we can modify the proof of this argument to say something about normal matrices, but it just is not as nice as what we can say about Hermitian matrices. And so once you see the proof of this, you might consider how you could modify the statement of this to give a statement about normal matrices rather than matrices that are specifically Hermitian. Okay, so I don't use it again, I'm going to throw the blue marker away. So why is this true? Okay, well first let Q1 to Qn be the corresponding eigenvectors let's say these are the corresponding eigenvectors. Okay, so that is A times QK is equal to lambda K times QK, and assume they are orthonormal. Assume that they are orthonormal. Now, the thing that we're assuming, we know, since A is Hermitian, we know they're already going to be orthogonal. We're going to assume that we've taken them and normalized them. Okay, and we can do that just by dividing by their magnitude. Okay, so we're going to assume that they are orthonormal. Okay, any vector Cn can be written as u, the sum, k equals 1 to n. I'm going to write it like this, ck times qk. And if we want, and we know what the CKs are, by the way. We know that CK is the inner product of U with QK, but that's not going to be something that is especially important for what we're doing right now. It'll come up in just a moment. CK is equal to the inner product of U and QK. Okay, remember that's one of the reasons we like orthonormal bases, is that the coefficients are very nice. Okay, so I haven't proven this yet. You probably already know it. But notice if I compute the 2 norm squared, this is just going to be the inner product of U with itself. So I'm going to have something like this. The sum k equals 1 to n, ck, qk. I'm essentially just proving something like the Pythagorean theorem or Plancherol's theorem. If you know those words, I hope you know the Pythagorean theorem. CJ, QJ. And sorry, let me try to not use angle brackets. Let me use the parentheses like the book uses. Okay, so what's going to happen? Well, I'm going to pull out a k sum, pull out a j sum, but it's all going to be 0 unless the two indices are the same, because qk and qj are equal to each other. And so what we're going to end up with here is ck bar times the inner product of qk with itself. And so this is equal to the sum k equals 1 to n of the modulus of the ck squared. Okay, so keep that in mind. U is written in this way. Then we know that the magnitude of U, the magnitude squared of U is given by this formula here. This is going to be very important. Okay, so here's what we're going to do. We're just going to compute this right here. Okay, so if we compute this, we're going to have A U, comma U. Okay. Well, I just computed U comma U. U comma U is equal to the sum of the ck squared, k equals 1 to n. Okay, now up here in the numerator, I'm just going to replace U with its expansion here. Okay, and so let me see if I can write it like this. So we're going to have A times the sum k equals 1 to n, ck, qk, like this. Okay, and then for U here, we're going to have the sum j equals 1 to n, cj, qj. It's best not to use the same index variable there and there, or it gets confusing, and sometimes you make simplifications that are not legitimate. Okay, so we're going to have k equals 1 to n, ck squared like this. Okay, now notice what's going to happen up here. Something similar is going to happen. Well, sorry, there's one important step. So I can now distribute this A to the inside here. And so we're going to have the sum k equals 1 to n, ck, A times qk. But what is A times qk? It's just lambda k times qk. So this is lambda k qk. Okay, now we're going to have something very similar happen. This is orthogonal. When we pull out the sums, the only terms that are going to survive are when k and j are equal to each other. And so when we do that, we're going to get the following. This is going to be equal to the sum k equals 1 to n lambda k times ck squared. Okay, so now what I'm going to do is this is I'm going to use the index here to be j, and I'm going to use the index here. I'm going to call that j now instead of k. Take the advice that I just gave to use different indices. Now, as far as k is concerned, this is a constant, so I'm going to move this kind of up here and write this in the following way. We're going to have the following is going to be ck squared divided by the sum of cj squared. And I'm just going to call all of these something new. I'm just going to call those bk. So again, I'm going to call this whole thing here, I'm going to call bk. So let me move things to the left here. So we're going to have k equals 1 to n lambda k. We're going to have ck squared divided by the sum of cj squared, j equals 1 to n. Now, this is a positive number, and ck squared is a positive number, so I can write this as like bk squared. So I'm just going to call those numbers bk squared. So we're going to have k equals 1 to n, lambda k, bk squared. Okay. Okay, here's something important about the bk's. The sum of the bk's, if you look at the bk squared, k equals 1 to n, they only have one constraint, and that is that they have to be equal to 1. Okay, so now the question is, we want to pick the ck's and therefore the bk's. If we want to pick the bk's here, that's what we get to pick. We're maximizing. Okay, we're maximizing. That means we get to pick the bk's. We want to maximize the bk's so that this is the biggest that it can be, subject to the constraint that the sum of the bk's have to be 1. Well, lambda 1 is greater than or equal to lambda 2, is greater than or equal to lambda 3, is greater than or equal to lambda 4, so on and so forth. So if I want to pick the bk's that maximize this sum, then I just want, b2, b3, b4 to all be 0, and b1 is just going to be equal to 1. Okay, because the lambdas here, right, are getting smaller. And so I want to put all of the weight on lambda 1. Okay, and so we know that this is going to be less than or equal to lambda 1. Okay, because the sum of the bk's add up to 1, and so this whole thing is going to be less than or equal to 1. Okay, if we want to be a little bit more precise about that, this sum is less than or equal to the sum k equals 1 to n. Lambda k's are all going to be less than or equal to lambda 1, because that's how they're, that's what this says. That's how we've ordered the eigenvalues. And this is times bk squared. Okay, but the sum of the bk squareds is equal to 1. And so this is equal to lambda 1. So this sum here is always going to be less than or equal to lambda 1. In other words, it says this is always going to be less than or equal to lambda 1. And indeed, if we pick b2, b3, b4 equal to 0, it's going to be exactly equal to lambda 1. Okay. All right, so that proves this inequality. But notice that we can we can continue this. So what is lambda 2 going to be equal to? Let's think about what lambda 2 might be equal to. So we can do something similar. What if we knew that if we only looked at u's that were orthogonal to q1? So in other words, what if we only looked at u's like this? So we've got the sum k equals 2 to n, ck, qk. Notice we can do everything. So this is going to be k equals 2 right here. We're going to have k equals 2 right here. This is going to be j equals 2, and this is going to be k equals 2. Okay? So in other words, in this case here, we're looking at all of the u's in Cn. But what if we restrict ourselves and we only look at the u's that are in the linear span of u2, u3, u4, and so on and so forth. So instead of looking at the u's that are in all of Cn, we're just going to look at the u's that are in the span of q2, q3, q4, and so on and so forth. And when we do that, this is the sort of sum that we're going to form here. And we're going to show that this is in fact less than or equal to lambda 2. And if we wanted to be equal to lambda 2, we just choose C3, C4, so on and so forth equal to 0. Okay, so now what this tells us is that lambda 2 is the max of u in Cn, where u, we're only going to look at u, not u in Cn, that's going to be a confusing way to put it. The maximum of u in the linear span of q2 to qn, and then we're going to have the same quotient, so a u comma u over u comma u, like this. Okay, but I'm going to think about this in a different way. So what we're really doing here is, okay, we're looking at u in a specific subspace. We're looking at u in a specific subspace. That is a subspace spanned by q2 through qn. But notice what we're doing. What this is really this subspace here is going to be if we look over all, so that this is an n-1 dimensional subspace. If we look over all n-1 dimensional subspaces, okay, if you look over all n-1 dimensional subspaces, the way that this procedure is going to work over here and get, again, if S is an n-1 dimensional subspace, the way that argument is going to work over there, the only way that argument is going to work over there is if all of the u's we're looking at are orthogonal to Q1. So what we want to do is we want to look at the minimum of all S such that the dimension of S is equal to n-1. Okay, so for every n-1 dimensional subspace, we're going to find the maximum thing here. Okay, if the vectors in S are not orthogonal to Q1, then it's always, this maximum here is always going to be equal to lambda 1. It's always going to be maximized when U is equal to Q1. Okay, so so that's not going to give us lambda 2, that's going to give us lambda 1. So therefore, we want to look over all of the n-1 dimensional subspaces, and when we form this maximum for each one of those subspaces, the smallest of that's going to correspond to the subspace that does not contain Q1. That is a subspace spanned by Q2 through Qn, and that is going to give us the lambda 2 eigenvalue. Okay, so how would we compute lambda 3? Well, if we wanted lambda 3, we would look at for lambda 3, let me change colors here. We would look at U in Q3, and then this would be n-2. Okay, and so in general, lambda k, we're going to look at the maximum of U in the subspace spanned by Qk through Qn and form this. Or another way to think about this is this min-max principle. So it's going to be n minus k plus 1. So we're going to look at all of these subspaces here. And essentially what we're doing, when we do something like this, we're saying we just want to look at the subspaces that are orthogonal to Q1 through Qk. And the only subspace that's orthogonal to Q1 to Qk is going to be this, this right here says we want to look at all of the subspaces that are orthogonal to Q1, Q2 up to Qk minus 1. the only subspace that is orthogonal to all of those vectors is going to be the subspace spanned by qk through qn, and that's why these two things are equal to each other. Okay, so this is called the Courant-Fisher min-max principle, and like I said, it's a very useful principle and a very, very cool idea that we can have here. Specifically this one. These are going to come in handy when we look at some of the analysis of convergence things. So again, keeping in line with what we've been doing, one of the most important things, I want you to have an idea for why these things are true, but I also just want you to know they're true, so there's sort of tools in your toolkit of linear algebra analysis of algorithms.